All right, time to talk about just some general laws that govern structural analysis. These should be familiar, somewhat covered in statics and mechanics of materials, but let's just explicitly review them so that we're all on the same page. By the end of this lecture, you should be able to define the principle of superposition and its limitations. Apply equilibrium in a coplanar structure and determine if a structure is determinate or indeterminate. And if it's determinate, figure out how to solve for the reaction forces using those equations of equilibrium. Also determine if a structure is stable or unstable. All right, so the principle of superposition is that you can take a structure that is subjected to several different loadings, solve for the different loadings, and then add together the resulting reaction forces and displacements. Gonna give you a minute to write that all down. So the principle of superposition is if you want to find the total displacement at a point in a structure, subjected to several external loadings, you're going to add together the displacements and resulting loads and resulting internal loads caused by each loading acting separately. So basically take the loads, break them up into something that you know the answer to, and then you can add them together. So a picture is worth 1,000 words, right? So let's say we have a simply supported beam subjected to a distributed load W and a point load P, and it displaces, has a deformed shape, something like that. It displaces some amount delta. Well, if I want to know how much it displaces, I'm going to take the two loads separately and find that displaced shape, right? Oh, let's say I'm not looking directly at where the load is. Oops. All right, if I look at the displacement at some point C, then I look at the displacement at C due to the distributed load. And similarly, if I solve for if I find the displaced shape of the beam under the concentrated load, I can find the deflection at C due to that concentrated load. So my deflection at C is equal to my deflection at C due to the distributed load plus my deflection at C due to the concentrated load. Right, so basically I say this is equal to this plus this. And I can do the same for the reactions. If I call this side A and this side B, I'm going to have a vertical reaction at A and a vertical reaction at B. And I can solve for my distributed load vertical reactions. These are my vertical reactions due to my distributed load. And I can also solve for my vertical reactions due to my concentrated load. Oopsies, that's a B. All right, so my reaction at A is equal to my reaction at A due to my distributed load plus my reaction at A due to my concentrated load, and my reaction at B is my reaction at B due to my distributed load, and my reaction at B due to the concentrated load. So that's all superposition is break it up into something you know and then add it back together. Now there are several limitations for the principle of superposition. Number one, your material must remain linear elastic. Meaning it must follow Hooke's law that we learned back in mechanics of materials, where stress is equal to my elastic modulus constant times strain. That's a linear relationship. And why is that a limitation on superposition? We're going to come back to this slide in a second. Why is that a limitation on superposition? Let's say I have a linear elastic stress strain response for my material, and I apply a load that results in a strain of 2%, right? Okay, my material is going to have a stress of 100 KSI. Let's say I apply a different separate load that results in a strain of 4%. That results in a stress in my material of 200 KSI. What if I want to add these two loadings at the same time, the one that caused 2% and the one that caused 4% strain? Well, that would yield a strain of 6%. And according to superposition, I can just add up those stresses, right? That stress would be equal to 100 plus 200. So I have a 6% strain, and hopefully it results in 300 KSI if I get to use superposition. And yep, 300 KSI. So, yep. So I can use superposition because I have a linear elastic material. Let's go back for a second. What if I have a non-linear elastic material? That means it's still elastic. There's no permanent deformation, but my stress strain curve is a parabola instead of a straight line. So I'm going to apply that load that results in a strain of 2%, and I get a stress within my material of about 210 KSI. I take that off. My material goes back to 0 because this is a linear elastic material. Or not linear, but it's an elastic material. And I apply a strain of 4%. Okay, I just applied 4%. It's going to result in a stress in my material of 300 KSI. So if superposition can apply, I can now add these two loadings together, the one that resulted in a 2% strain and the one that resulted in a 4% strain. So I now have a 6% strain. Okay, if superposition applies, I can just add together those two responses, right? I should have within my material 210 KSI plus 300 KSI, which is 510 KSI. So I go and I look at 6%. No, if I apply 6%, I should only have about 370 KSI. So superposition is overestimating how much stress is actually felt by my material due to its nonlinear response. So you can't use superposition for a nonlinear elastic material. And finally, what about if I have an elastic plastic where the first little bit is elastic, linear elastic, but after that we hit a yield stress and we have a plastic material? So again, I'm gonna apply a loading that results in 1% strain. And okay, that gives me a stress of about 25 KSI in my material. I take off my loading, go back down to 0 because I'm still in my linear elastic range. Now I'm going to apply a strain, a loading that results in a strain of 2%. Right here on the cusp of linear elastic and plastic, but I'm still elastic, and that results in a stress of 50 KSI. Say I add those two separate loadings together. That would give me a strain of 3%. So if I take my 25 KSI and my 50 KSI, 75 KSI. So if I apply that 3%, I should have an internal stress of 75 KSI. So let's see, 3%. Oh, nope, that's about 60. So again, I'm overestimating because I'm assuming that I'm a linear elastic material. And also, if you had applied, right, if we'd applied that 3% and then took it off, it would have some permanent deformation already because of the elastic plastic response. So it's just highlighting why we can't use superposition for anything other than a linear elastic material. If I go back to my superposition limitations, I have one more. superposition only applies to small displacement. What does small displacements mean? Let's look at if we had a cantilever beam subjected to a concentrated load. Would result in a reaction force over here of P and a moment M, which would be P times the length, right? And in applying that concentrated load, I have a deflected shape like that. And my load follows my deflected shape. If I have a really large displacement and my load follows the beam, well, now I kind of got a horizontal component to my load. It's no longer strictly vertical. So if I were to solve for the moment, the reaction moment, not only do I have to take into account the Py, right? My moment reaction force would be Py times my length, but I also have a moment of Px times this deflection. If my displacement is small, then my moment is essentially equal to P times L, because basically that Py would be essentially equal to P, and Px would be very small, the deflection would be very small. But if I have a large displacement, then I have to add in that P delta effect. So my equations of equilibrium that I'm used to would not be correct. I'd have to know what that deflected shape is. And if I have a small displacement due to two different loadings, that's fine. But what if one is a large displacement, one is a small? Have to take the deflected shape into account. So superposition is no longer applicable. Okay, so that's the summary of superposition. Basically just means you can add up the responses to different loadings as long as you have a linear elastic material and you're not having huge displacements. This should definitely be a review. I hope you understand. I hope you remember. But let's just talk about what laws that govern structural analysis. Well, equilibrium. You know, everything must stay in equilibrium. So the equations associated with those equilibrium equations for my forces, my sum of the forces in the x direction is 0. Sum of the forces in the y direction is 0. Sum of the forces in the z direction is 0. Moments. Some of the moments about the x-axis is 0. Some of the moments about the y-axis is 0. Some of the moments about the z-axis is 0. These laws apply to both the entire structure and any single part within a structure. If a structure is made of multiple parts, such as multiple columns, multiple beams, multiple braces, different truss members. If there's more than one part, if there's a joint separating something into more than one part, these equations apply. Okay? Making a note for myself. Okay. So if we have a coplanar structure, we can have coplanar equilibrium. Coplanar meaning we're in 2D, so we're on a piece of paper. We're not out in space. Our entire structure is in the same plane. So if we come to 2D, we have, right, X and Y, and then Z is in and out of the page. So my governing equations reduce to sum of the forces in the X, sum of the forces in the Y, and some of the moments about Z. Let's just give a quick little example. Here I have a beam subjected to a distributed load W. The beam has a length of L. And if I look at the entire structure, I can have, I can solve for the forces in the x direction equals 0 because there are no forces in the x direction. Right? If this is A, my reaction at A in the y direction, reaction at B in the y direction. And this is a pin over here, so it has a horizontal component, but we don't have any type of horizontal loading, so my horizontal reaction at A is going to be equal to 0 because I know that the sum of the forces, if I make right positive, but it doesn't matter. Negative over 0 is still 0. If I solve for the sum of the forces in the x direction, I find that my horizontal component is equal to 0. If I solve for the sum of the forces in the y direction and I have up as positive, that's going to be equal to 0. I have in the positive direction the vertical component, the y component of my reaction at A, the vertical component of the reaction at B, and in the negative direction I have W times L. If I look at the moments, let's say I take the moment about A, counterclockwise is positive. I want my moments about A equal to 0. I have WL squared over 2 as my moment due to that distributed load. It's acting clockwise, so it's negative. I have a reaction at B, force times the length. It's acting in the counterclockwise direction, so it's positive. So there's one equation of equilibrium. And if I do the sum of the moments at B, the same thing. I have now my distributed load moment is acting positively, but my reaction at A times the length is negative. Now this is the entire structure. If I just look at part of the structure, alright, I'm gonna take this. Alright, that's for the entire structure. Now I'm only gonna look at the part of the structure. I can solve for my internal loadings as well. If this is some distance along the length X, still have my distributed moment, my reaction at A. Why did I make that point that way? It doesn't actually matter. All right. You can assume it's positive. And then just let the math tell you otherwise. And then internally, I have a shear and a moment at this point O. And I also have a axial load. Again, I'm going to solve the forces in the x direction. Right is positive. I have RAX minus my reaction at A in the horizontal direction and my axial force at O where I cut my beam. And of course I solved earlier and found that RAX is 0, so the axial force is 0 as well. But this is just an example. If I solve the forces in the y direction with up being positive, I have RAY acting up, I have my shear acting down, and I have W times, not L, W times X, right? That's the length X, the attributed load along the length X, both acting down. Can also solve for the moments at A. In the negative direction, the clockwise direction, I have W x squared over 2 plus or minus my shear times that distance x plus my moment at O if I solve for my moments at O equal to 0, I've got my moment at O plus W, Wx squared over 2 minus RAY times X. If you need more help with those equilibrium equations or solving some of the problems on the homework, let me know. I need to go check the discussion board and see if anybody's asked any questions. Hopefully you at least touched on this in mechanics of materials and statics. So just examples of equilibrium, both of the entire structure and along the length of the structure, within the structure. Determinacy. I know, keep looking up how to write this word. We have two types of determinacy. Either a structure is statically determinate or statically indeterminate. So if a structure is statically determinate, I keep wanting to add an N in there. It's not. Statically determinate. It means I can use the equations of equilibrium, and that's all I need in order to solve for the reaction forces of a structure. I don't need any more information. So equilibrium equations give me enough to solve for my reaction forces and determine their values. If a structure is statically indeterminate, the opposite is true. If it's indeterminate, equilibrium equations are not sufficient. I need more information. So I'd either need to know something about the displaced shape or make assumptions about the displaced shape, and go from there to determine my reaction forces. If a coplanar structure, let's see, for a coplanar structure, my equilibrium equations are, I have 3. We just talked about them. They are some of the forces in the horizontal direction, some of the forces in the vertical direction, and some of the moments about Z. Those are my 3 equilibrium equations. If a structure has n parts, and R number of reaction forces, if R is equal to 3 times n, that's my 3 equilibrium equations. That means my reactions is equal to the number of equilibrium equations times the number of parts, because I can have static equilibrium for each individual part. Now, this isn't just cutting a beam and saying, oh, 2 different parts. This is if there were 2 different beams and they were connected by a joint. A beam connected to 2 columns, that would be 3 parts. So if a structure has n parts or R reaction forces, if R is equal to 3 times n, my reaction force is equal to 3 times the number of parts. It's statically determinate. If my reaction forces that I need to solve for is greater than 3n, because I only have those 3 equilibrium equations and I can only apply them n times. If I have more reaction forces than I have equilibrium equations, then it's statically indeterminate. So R equals 3n. I only have enough reaction forces that I have applicable equilibrium equations. I can solve it using only those equilibrium equations. But if I have more reactions than I have equilibrium equations, I'm going to need some more information. I can't determine it using only static equilibrium. I'm going to have to figure something else out. So if we talk about an example, let's look at this beam and figure out if it's statically determinate or indeterminate. If it's indeterminate, how many degrees of indeterminacy? So let's see, I have 2 pins. So if this is A and this is B, I have a vertical reaction force and a horizontal reaction force at A. I have a vertical reaction force at B and a horizontal reaction force at B because these are both pins. So how many reactions is that? 1, 2, 3, 4. R equals 4. That's my number of reactions. How many parts do I have? Just one, right? It's just one beam. N equals 1. So if I do R and compare it to 3 times N, which is equal to 3 times 1, which is equal to 3, R is greater than 3. R equals 4, right? R equals 4. 4 is greater than 3. So this is a statically indeterminate beam. And its degree of indeterminacy is 1, because 4 minus 3 is 1. My degree of indeterminacy is R minus that 3n. That means I only need one more piece of information to solve it, but I don't have that information. So now the question is, what can I do to make this beam statically determinate? Not that this is something that you can just easily do, but I'm just posing the question. Hypothetically, if I could just change the supports, what could I do? Well, I only need to get rid of one reaction to make this a statically determinate. I have one more reaction than I have equations of equilibrium. So if I get rid of one of those reactions and I have 3, then 3 is equal to 3, right? So I could remove one of my pins. Remove a pin. And make it a roller. A real roller only has one reaction that's in the vertical direction, doesn't have the horizontal component, and that would look like, right, if I changed A, it would look like that. Oops, go back. Trying to how did I get it to make a bigger page? Anyway, right, if I did that, I'll draw right here, right? Then my only reactions would be a vertical reaction at A a vertical reaction at B and a horizontal reaction at B. 1, 2, 3 reactions. One part, 3 times n is 1. Or I'm sorry, 3 times n is 3. So 3 reactions, 3 equations of equilibrium. And this right here with a pin on one side and a roller on the other is called a simply supported beam. You see it all the time because it is a statically determinate structure. So everybody draws them. They're fun. They're useful. So that's an example on determining if you can solve it using only equilibrium. So it would be statically determinate. Let's quickly talk about stability. What does it mean to be stable? Means you're not moving, right? You're unwavering. Not moving significantly. Significantly. How do we figure out if something is unstable? We can use those equations before. Now we're going to relate our number of reactions to our number of equations of equilibrium. If we have too few reactions, we are unstable. If you have enough reactions, or even more reactions than equations of equilibrium, you could be unstable if all of your reactions are concurrent or parallel, and we'll look at what that means. So if either of these situations exist, if you don't have enough reactions or all of your reactions are concurrent or parallel, this means that your structure is improperly constrained and it's unstable. That says improperly constrained. So what does that look like? There's two different classifications. One being partially constrained, which is the first one. If you're unstable if you don't have enough reactions. So let's take a look at this angle piece. It has a angled load on it. And what are the reactions at the point A? Well, it's got a vertical reaction. And it can have a moment. This is a glider. Oops. Yeah, okay, that's counterclockwise. A moment reaction. But can it move horizontally? Yes, it's not being held in place horizontally. So if I apply a load that has any type of horizontal component to it, this thing is going to move. right? If I break down my angled load into a vertical and a horizontal component, it is going to move to the left in this case. So if I try to take some of my forces in the x direction, and have them equal to 0, the only force I have is this negative px. I don't have a restraint down at the bottom, or a constraint. So the only way this works is if there's no horizontal component to that load. So we'd call this partially constrained because it is unconstrained in the x direction. Now, what about that improper constraint concurrent reactions? Here I have a beam supported by 3 rollers. 2 of the rollers are on angles, are on slopes that have the same angle. Right? So if I draw my reaction forces, I'm going to have a reaction force at B in vertical direction, and then I'm going to have a reaction force at C and a reaction force at A that are basically equal but opposite, right? So if I apply a load and I want to solve for equilibrium, first of all, it's going to be statically indeterminate because I have too many reactions. But second of all, if I solve for my moments about this point O, where if I draw a line, these would all meet. If I take a moment about O, I've got my reaction force at A, but there's no moment arm. So reaction force at A times 0. A reaction force at B. Again, there's no moment arm because if I just draw that line up, right, there's no moment arm. My reaction force at C, again, since this is parallel to the line that we're taking the moment about, I have no moment arm. I do have, though, if I'm taking about O, P times D, that force, right? P times D. If I cross those out, the only way this works, I end up with P times D equals 0. The only way that works is if there's no force. Well, what good's a structure if you can't apply a force to it, right? Let's say I did apply that force. Probably have something like that. And then my beam would just fall down. Right? It would pivot about that B. And it would be unstable. This is an example of your forces being concurrent. All right. that means that all of your forces, if you draw a line, will meet in one spot. The vectors along which they're acting will all meet in one spot. By improper constraint, this is going to be similar. My last example is similar to the glider. I have 3 rollers here. Their reactions are all in the vertical direction. So if I break this force down into its components, I take some of my forces in my x direction. The only force I have in the x direction is that load being applied, the horizontal component of that load. So that only works if I have no load, or if I have a perfectly vertical load. So this is unconstrained in the x direction, right? If I do apply that angled load, what happens to my beam? It goes whoop, right? Just slips on by. So finally, just to sum up how we're going to approach analysis of structures. 1, draw a free body diagram. Right, it always starts with free body diagrams of your entire structure. And individual parts, if you'd like. Definitely start with your entire structure, and then you're going to maybe break it down into individual parts. 2, count your equations, your unknown equations, or your number of unknowns. Sorry, like your reactions. And compare to your number of equilibrium equations. Which would be 3n for coplanar structures, probably 6n for not for 3D structures. And finally, write your equations and solve for your knowns if you can do that, if it's statically determinate. If it's not statically determinate, then we have to do some more advanced methods, which we will get to at the end of the class. So draw your free body diagrams, draw them of your entire structure and individual parts if you need to. Count your number of unknowns, compare it to your number of equilibrium equations. If you have enough reactions, if you have R equal to 3n for a coplanar structure, then that means it's statically determinate, and you can write your equations and solve for your unknowns using those equilibrium equations. If not, we'll have to go to more advanced methods. So with that, we've finished the introduction to this class, and we'll be moving on to statically determinate trusses after this. Thank you.